able to listen to me, right? I will not speak in a very high pitch, but I will try to do as best as possible. Okay. So, yeah. So, Professor Pritimoy, shall I start, or let me know when I should start?
Yes, sir. Yes, sir. Yes, yes. Just you can start. Okay.
Why I can start, right? I can start
Yes,
the
sir.
lecture.
Yes, sir. Yes, sir.
Fine, fine. So, yeah. So, what I will discuss today with all of you is that means you know that okay, quantum computing. Quantum computing is one of the important technology aspect or technology area where we are having a paradigm shift of computing, both in terms of computational algorithms as well as in terms of computing infrastructure. Okay, so today what I will discuss with all of you is that means what is this quantum computing? What are the basics of this quantum computing, and some of the key aspects of quantum computing, and try to motivate you that what are the things are possible, and there is a big enough pie for all of the researchers in computing, okay, and electrical engineering and physics and mathematics and statistics, okay, to contribute in this a great domain of quantum computing, okay. And as you know that in India, presently in our country, we are going to the National Quantum Mission, which is really a fantastic thing to happen, okay. And there's a immense push in our country to build the various forms of quantum technologies, uh, okay, with the researchers of the country, and various institutes and various researchers have already started working on that, okay. So so might be some of you are connected with those activities. If not, okay, right, I hope that in the very recent time you will get the opportunity to do so. But today's lecture, I hope that I will be able to um, make some of the very basic understandings of quantum computing clear to all of you, and okay, right, and obviously to motivate you in this domain. So I will start my lecture. I'm just keeping the video off at present due to the saving the bandwidth and giving the maximum bandwidth to my presentation. Okay, but I will take around a lecture of 1 hour plus, where I will pause a bit in between, so that you all can, okay, ask me questions. So maybe now it's almost 6:25. Maybe I will give a pause at around 6:50, and then I will close around 7:20. Then I will expect the questions from all of you. Okay, so let me start my presentation. Okay, yeah. So I hope my okay, I hope my presentation is visible to all of you, right?
Yes, yes.
Okay, so the title of my presentation is a very basic title, okay. So I am obviously presenting this as a perspective of computing researcher. As a researcher in computer science and engineering, obviously there are different perspectives of quantum computing that is all converges in the same plane, but there are different perspectives of quantum computing. Okay, for the people in electrical engineering, in the physics, chemical sciences, as well as mathematics and statistics. Okay, but let me focus more on the computing part, because that is the part what I do. Okay, as a research, and my research on quantum computing is almost touching 21 plus years. Okay, and yeah, so that's why I feel really very uh, okay. That means I really feel very honored when I want to present something on quantum computing, because this is core of my research. Okay, so let's move on. So what we look into quantum computing is a paradigm shift, as I mentioned. Okay, so what is this paradigm shift? We had started computing from the early, okay, 19 around, I think 1920 or 30, right? Okay, the concept of computing came, right? And we had the electromechanical machines which emerged around 1940, 50, okay? Uh, okay, and I was lucky to, so on the extreme left, you have the electromechanical computing, which were not computing what we say today. They were basically the counting machines, okay, where we can actually give the input, and they could count in an automated way, okay, and give us the results. And I was very lucky to be a part of Princeton University as my postdoc, and as a visiting professor in Cambridge. And both the institutes have the Museum of Computing, and in that you can get to see that. Okay, but let's move on. Then came the age of transistor, which was the actual computer, which we are now working with. And this computer started from around 1960 plus, and is still continuing. It's a fascinating technology, and I also work in the domain of VLSI design, and I know how fascinating technology it is, right? At the present form of the transistor, which was discovered in 1947, right? A big junction transistor, which size was of the order of centimeter, a single transistor, which was discovered in the Bell Labs around 1940, mid of 1940s. Now, the transistor sizing about the latest technology, which Intel and other AMD, okay, they are working with, they are almost touching 1 nanometer transistor size. So imagine a few centimeters to 1 nanometer, right? The size of transistors. And due to this high reduction in the size of transistors, we now have almost a trillion transistor in a chip or a die, which is of an area of something like 3 millimeter plus 5 millimeter. Okay, and this 3 millimeter plus 5 millimeter chip is now housing almost trillion transistors, and this is making our computing very different, right? The computing what we used to have during our university days, maybe almost 30 years ago, okay, right? Those computers, compared to the smartphones what we have, right, in terms of memory and computing, maybe our smartphones are almost 10x capacity of the big box computers, which we used to have almost 20, 30 years ago. And that is because we are having multi-core chips, many core chips, SoCs in our hardware. And so the entire system of computing is now converged to a single chip. You can just have a single chip, right? And that can do an enormous amount of computing, because that chip consists of multiple cores, the memories, and all the peripheral electronics, RF, okay, right? Okay, for communication and computing, and we can integrate it on a single chip, okay? And that's fantastic technology of VLSI. In fact, it's not VLSI now, it's ULSI, ultra large scale integration. And that integration have paved the path so that now devices has been connected with the things, Okay, we have the technologies like IoTs, okay, right, where we can have a very, very small size chips and actually doing not many things for us, okay? But now if we go further, right, on the extreme right, what I show, okay, if we go further, what we see is now as the transistor size almost touching 1 nanometer, which means that the transistors are now having almost a depth of one or maybe a few atomic layers in the transistor. Okay, now this is very interesting. Okay, this is very interesting because the transistor squeezing down the size of transistor is obviously pushing us to the limits of matter, and that limits of matter is the atomic layers. Okay, atomic layer depth transistors. Now, can we go farther? Now, if we go farther, the atomic layer, what we hit is basically the subatomic layers. And subatomic layers of the matters consist of electron, proton, neutron, right? And can we do computing with those atomic layers? If we can do, then it is called quantum computing because the operations of these subatomic states, okay, and operations of the subatomic states are governed not by the classical laws of physics, they are governed by the quantum field theory. And the energy states or whatever observables of these particles, like energy states, like the speed states, okay, like there, if we go to further, the optical equivalent of these are photons, okay, the polarization states, okay, the direction of the spin, all these are quantized parameters of the matters in this level of matter, and hence it terms as quantum computing because quantum computing involves the matter of the subatomic states and tries to exploit their quantum properties and tries to transform the quantum states from state 1 to state 2, which defines a computing. Actually, in transistor also, if we look into the fundamental, what we are doing, we are actually pushing the state of a transistor from 1 to 0 or from 0 to 1. And that 1 to 0 to 0 to 1 of the transition of the states ultimately defines the computing. Okay, so similarly, but we know that the state from 0 to 1 and 1 to 0 are very, very broadened states. Okay, so we cannot have those quantum phenomenal existing on the states. But in these particular subatomic states of matter, we will soon come up that they are quantized. Inherent quantum properties will give us a lot of other benefits which we're not able to exploit in the classical transistors, in the classical computing. And that's the magic of quantum computing, I say, okay? And controlling that magic is called the game of quantum computer, okay? So let's move on from here, okay? Before getting into the details of quantum computer, let's try to understand, let's have a feel of a quantum computer, okay? I don't know whether some of you were there in the India AI Impact Summit. If you were there, I don't know whether you have visited the stall of Fujitsu, right? I was there in this India AI Impact Summit as a speaker in one of the sessions, actually 2 of the sessions. Okay, right? And I was very highly motivated to see the Fujitsu, the Japanese, you can say electronics, high performance computing organization, okay, have showcased a miniature model of quantum computer. And this, what you see in the figure, is a quantum computer, right? And this is called this is obviously of a specific technology. Sorry due to my bad voice, I'm just having a warm tea, okay? Okay, just excuse me. I'll continue the lecture while I'm having the tea, okay? So so this particular image is also a model of quantum computer. Okay, I will come to the story later a little bit, but let's try to say what is this model. If I use a pointer, let me use a pointer here, okay? So So the main question from a computer engineer or an electrical engineer will come up that, Professor, where is the chip? Okay, we know that you are telling of a computer. So computer means there should be a processor chip. Okay, now the processing chip in the case of quantum computer is called QPU, quantum processing unit, right? And the scale of quantum processing unit is defined by the number of qubits this quantum processing unit has. Again, I repeat, okay, the processing element for a quantum computer is termed as, you can take a note of this, who has some pen and paper. Okay, it's called QPU. It's called a quantum processing unit, and the scale of the quantum processing unit is defined by the number of qubits this QPU has. Okay, and if you look into this figure, the QPU, the quantum processing chips, sits just at the center of the base, the lowest base of this particular entire system. And you can tell me that, sir, why there's so much a bunch of wires? Okay, and that's the interesting thing, right? This bunch of wires are basically the signal channels which controls these qubits, both in terms of initialization to the quantum state, doing operations, transformations of the quantum state, and trying to do a readout of the quantum state to evaluate the result. So you have a hell lot of connecting microwave pulse signal channels, and these are superconducting qubit. So the control signals and microwave, if you change the technology, you can come with the technology like ion trap, where you use the lasers, right? You can go for a photonics, where you use again the lasers. So there are, depending on the technology, right, you will have the different types of control signals. Okay, but now come back to this diagram. This diagram, as I say, this is the quantum chip QPU. Okay, I cannot tell how many qubits, but if we look into the present IBM, right, who have started this quantum computing, I'm not doing any propaganda of IBM in here, but I am very lucky to work closely with them. Our group got the IBM Research of Access Award, the first group in India in 2021, and so we are very honest about what IBM is doing in quantum computing, and very well connected with them. Okay, and so IBM started this superconducting qubits, and we know that in India, Quantum Valley, we will have a large facility of this IBM superconducting qubits managed by TCS, supported by the government of India. Right, not many things goes to happen, but again, to cut it short. Okay, let's try to come back to the context here. So the context here is that, okay, we have understood that, okay, the present size of the qubits, number of qubits in a QPU are almost crossing hundreds. Okay, it's almost 120 plus qubits. Okay, the technology has scaled up such a way that almost 120 plus qubits are now being are being available as single QPUs, and now the next level of is that increase the qubits in a single QPU, and also make a distributed connection of multiple QPUs, and try to escalate the number of qubits available over 5,000 is the target in the next 1 or 2 years. And once we reach the targets of 1 or 2 years of 5,000 qubits, we will be, actually the classical computing will be endangered in many applications. Okay, again, to cut it short, just to close this discussion, that apart from that, there is also a typical structure which has been taken up here. Okay, you can see a cover. This cover is because these quantum states are very fragile, and you cannot expose them to the external energy sources. So the entire quantum chip, which says here, needs to be sealed, okay, against the external energy sources, and they should be cooled down to a very low temperature so that they don't have their internal energy oscillations. Any thermal energy generates oscillations internally, and that will disturb the state of the system. Okay, so the only oscillations or transformations of the states ideally will be done by the control signals which hits the qubits. So to make all these things ensured, this is called cooling chamber, called a dilution refrigerator, which actually maintains almost a 0 Kelvin temperature. And once we push this, push this big box down, then it becomes sealed from the external environment and sits in this very cool temperature. Okay. I will also tell you that though this is a model you can see in Fujitsu, but I was very lucky to visit the IBM Watson lab in last July 2024, where I was invited by IBM to visit their lab and to have a research meeting with some of their very senior research members. And I was very lucky to see this computer, see this computing server of IBM at IBM Watson, which is around it's a place called Yorktown, almost a 1-hour drive from New York. And I was very lucky to see that. They are now housing around 3 of these servers in a distributed way, and each of the servers are having 3 QPUs, and each of the QPUs have around 120 plus qubits. So almost they are touching 1,000 qubits now at present using a distributed facility. Secondly, I was also invited by NVIDIA San Francisco to have a meeting with them, and NVIDIA successfully demonstrated in a conference called DAC, which is a very, very prestigious conference. And I was a part of the DAC 2025 as a program committee member. And I was a discussion with NVIDIA. NVIDIA presented in the DAC their paper, how they connected their GPU with these QPUs. Though the QPUs were not from IBM, obviously, NVIDIA will not have the QPUs from IBM. They had the QPUs from other organizations, other manufacturers. It's not that only now IBM is across the world is manufacturing QPUs. There are at least 4 or 5 other strong organizations who also have the quantum chips. And there are a good number of labs, around 10 plus labs across the world, right? And India is also having a lab at TIFR where they have built the quantum qubits. So depending on the different numbers of qubits, it varies from lab to lab, but commercially available chips are now there. TCG Crest in Kolkata has set up a 5-qubit quantum computer lab, right? And you are right. You will be very. That means some of you can visit that with a proper communication with the TCG Crest. So I think I have a little bit motivated you that when I was doing PhD 2005 at ISI Kolkata, I wouldn't have the opportunity to understand what is a physical quantum computer, though I was doing a lot of work on logic synthesis of quantum computers. But now I think who you are, that you are now very lucky to see that real physical quantum computers are there, and people in every day are trying to progress in this technology. Okay, now let us move on. What is this quantum states? So when we look into this quantum computing machines, why are they so special? They are special because the computing itself is very different. I will explain it. Normally when we look into the classical computing, it's we call a processor pipeline. We say that the data comes from the memory, and then the instruction is decoded, and then based on the instruction decoding, the operations at the ALU are performed, and after the operations of ALU are performed, the result either goes back to the register, it's called a write back, or it goes to a memory. Now this is a normal pipeline, and you define 4 or 5 stages of that depending on the hardware architecture. Instead of a simple ALU, you can have a vector processing unit, and all these things you can do. But still, it is a pipeline from very simple pipeline to a complex pipeline. A pipeline works like this. But in quantum computer, it's a different way. It's not a pipeline. It's not that you have a data in one box and processing is done on the other box and the result is transferred to other box, which is why the pipeline works in classical computer. Data is in the memory, in your RAM memory. Processing is in ALU. From RAM to register transfer, register to ALU transfer, ALU to register transfer, or memory transfer, and then memory transfer. These are because all these are in distinct boxes. In the quantum computer, the box is the same box of qubits, nothing else. Okay. And the qubits are initialized, represent the initial state of the machine. Okay. There are operations which transform these qubits. In the quantum state, transformation of the qubit happens. So the qubits are quantum states. Okay. And this quantum state transformations happens for the qubits. Okay. And that after the transformation, we have a readout to understand the distribution the transformation has generated. And once we sample the distribution, we get the result. So you see, it is very close, like an in-memory computing. You don't have any other computing resource. You have a single memory which initializes the data, and on the memory only we transform the data. Okay, and then we read out from the same memory. So this is why it's special of the quantum states. Okay, and the second one is that this type of operations leads to an exponential speed up. I will very soon explain why the exponential speed up. Okay, and this exponential speed up is a real power of quantum computers. That why it has been told that a quantum computer, if comes in a proper scale, will surpass the classical computer in terms of speed. And apart from computing, there is also very, which I will not touch in this lecture, there's a very, very interesting phenomenon going on the communication side. Quantum communication requires less qubits, and quantum communication is now an established technology. Though quantum computing will still have to improve a bit in terms of number of qubits we can have, and then only it can challenge the classical computer. But quantum communication, it doesn't require such number of qubits. It can work on few qubits, and it's already proved that quantum communication in terms of the quantum teleportation and quantum key distribution, right, works so good. And it has been established, links have been done, right? If you go to DRDO lab, okay, right, they have established the link. If you go to the Raman Research Institute, they have established the link. If you go to the IIT Delhi latest research going on there, they have also established the link. So these are the okay, so these are the national level very good examples that how the quantum communications are made to work. Okay, internationally there are a lot of services have been generated now. Okay, people are offering services on cloud, okay, for quantum communication, and this is so interesting. Okay, but I'm not touching this quantum communication in this lecture. Okay, now I will not get it. Okay, so computing networks have been touched. Security is one of the important thing. Quantum communication involves an inherent security because due to the uncertainty in the quantum state, right? Quantum state, we will see today that in this lecture, those who are going for the first experience of quantum computer, we will see today that it's very difficult to decode a quantum information, right? In terms of knowing its value, as well as knowing the basis on which it should be measured. So these two simultaneous knowledge is very difficult to be gathered, and this is the uncertainty in the quantum state. And so if we convert the data to the quantum state, getting the data through attack scenarios are very difficult. And if attack also happens, the error rate is so high that the information of the attack to the sender and receiver is being communicated or is automatically known immediately when the puncture on the channel is done. And that's why quantum security is so important. And many of the national organizations have established the quantum security backbones. Okay, quantum sensing is a very important part. Sensing is very important part nowadays, because sensing gives us the information of what is at present happening in an environment. Okay, and the limitation of our present sensing is that though we have a lot of sensors, but the challenge is that the sensors are still not able to detect very, very low amount of change. Sensors are fine when there is a good amount of change. sensors are fine, right? Because these sensors are works on classical limits, where it require a good amount of energy to actually do the change of state. Whereas quantum, as I said, quantum energy states are very specific, and this quantum energy states change can be done with a very low energy change. And so people are employing quantum sensing to understand very details of the change, and also very low energy changes, right, in the environment, which will be possible to detect a large catastrophe like earthquake, where the signal comes, but signal for a signal from the earthquake center to propagate that to a good amount of strength and hitting the other adjacent area requires a time. But if we can have a quantum sensor, we can record the fluctuation, a minute change in fluctuation very quickly, and we can have a larger time to actually take care of this particular seismic signals. Also in defense, a lot of low energy signals, they need to trap, and quantum sensing can be a very good thing. And so people are doing very good work in quantum sensing across the world. Okay, but I will also not touch here, okay, in this particular lecture. Now, just to motivate you, as I said, that as we are moving across time, we are somewhere, but maybe the next level, we are almost touching the 500 qubits quantum computers, where we will surpass the classical computer at the present state. Okay, and this will lead us to think about security, to think about optimization in a much powerful way than also machine learning. I'm not telling machine learning directly here, okay, because we need to look into more on that. But optimization, definitely yes. Okay, factorization, definitely yes. Okay, some of the NP problems, definitely yes. Okay, and that will surpass the classical computer. And so people who are not having quantum computer, vis-a-vis the people having quantum computer, will have a different types of advantages. And that's why every country, every organization is moving towards developing their own quantum computer. Okay, I'm also telling that there's a immense growth in the funding, in terms of the market trends and the finance in quantum computer. And so this is very interesting, right? And I think now we require manpower to support all these activities across organizations. And hence I say to all my colleagues in academia and the various institutes across the country and the world, that please try to focus on quantum computing course, and try to offer quantum computing course, okay, right, in the specific disciplines where we can find good students who can absorb this course, because we require a lot of manpower to handle the quantum computing activities in our organization in the country. Okay, now I come straight to the technology. Okay, so straight to the technology, what I say is that, hey, if I try to look into the comparing the classical computing with the quantum computing, one hand and the other side, right? We all know that classical computing is defined by the computing units called the bits. Okay, and what is bits and how the computing works here is that our data, okay, whatever form, are encoded in the logical states, and the encoding is done to the binary encoding of generating the data in the binary pattern of 0 and 1. And then the computing means we try to change the values of this data through some logical arithmetic process, right? And ultimately we come to another state of the memory, which is also comes from the Turing machine concept, state of the memory, which it presents the ultimate outcome of the computing. And this can be done in various stages, and various memory blocks. Each of the memory blocks can be your data variables, okay? Now, when we look into the quantum computing, we tell it's not bits, it's called qubits. They're called quantum bits, right? And this quantum bits is very different from classical bit, okay? Why? Because classical bit is stored with either value 0 or either value 1. You cannot have a bit. If you pick a bit from a memory, okay, you know that I have to find out whether it is 0 or 1. That's all I have to know, okay? But when we look into the classical quantum bit or qubit, it has 2 probabilities, okay? Because you see, there are large number of quantum states, quantized states, okay? I've shown a specific quantum state, and there can be very, very large number of quantum states where the qubit can exist. Each of the smaller dots are the possible quantum states, and there can be more quantum. This is just a simple example of some of the few quantum states what qubit can have. Though within those 2 quantum states, within all possible quantum states a qubit can have, there are 2 distinct quantum states which are very, very far off, which are perfectly aligned to the basis, which is called 0 and 1. So we have a 0 and 1 state in quantum in a qubit. But apart from that, there are also other possible states. Generically, a qubit stores 2 values. One is its probability of measuring 0, and one is its probability of measuring 1. Okay, so this is the difference of a qubit from classical bit. Again, I repeat, the qubit stores 2 values. One is its probability of measuring 0, and one probability of measuring 1. So normally represented by a state psi. I don't know whether I have an example to that. Yeah, let's come to here. So this is an example psi, okay, which is a quantum state, a single qubit quantum state, okay? And this particular sphere, which is a 3-dimensional sphere, is called the state space of a qubit. And the state space of a qubit means what? What is the state space of a system? Okay, just coming to the vector space concept, okay? And that's why the linear algebra plays a so important role to learn quantum computers, okay? So the state space of a system means the entire space where any point in the space can be a probable state of the system. So if we look into this entire surface of the Bloch sphere, any point in the entire surface of the Bloch sphere can probably be a quantum state, okay? And that generic quantum state, a single qubit quantum state, generic single qubit quantum state, will be represented as a state called psi, equivalently represented as a vector psi, which is a point, which is the vector from the center of the Bloch sphere to any point on the surface of the Bloch sphere where I represent the psi. And if I look into the state, so a state space should have a state parameters. These parameters means that if I change the values of these parameters, the system will move from one state to another state in the state space. So if we want to change the state of a qubit, which is presently here, and I want to take the state on another point on the surface, suppose here, what I need to do? I have 2 parameters here. One parameter is the theta, which is the angle, the vector psi. It's called a state vector of the single qubit state psi. Okay, the state vector makes an angle with the z-axis, one parameter theta, and another parameter phi. This state vector with the projection of the state vector makes with the positive x-axis. So if you are moving the state or transforming the state from point 1 on the surface of the Bloch sphere to point 2 of the Bloch sphere, you're either changing theta, or you are changing phi, or you are changing both, right? And this 0 and 1 are called the basis states. Means any state, basis state is the fundamental concept of the linear algebra state space concept, okay, or the basis vector concept, which means that any vector in this state space can be represented as a projection, as a combination of components across the 0 and across the 1. Okay, so that is most important to understand, that any qubit, the generalized qubit, obviously you can have an entirely qubit to 0 and entirely qubit to 1, where if I make the qubit to 0, then the corresponding projection on the 1 is completely 0. And if I make a qubit state completely 1, then the corresponding projection on the 0 is completely 0. It is a pure 0 or pure 1. But generically, a qubit state can be any point on the Bloch sphere. And so it is identified by theta and phi. And so we try to define it in terms of the components across 0 and 1. And the component across 0 is cos theta by 2. And the component across 1 is sine theta by 2 to the power I phi, which means that any psi in general has a amplitude across 0 and the amplitude across 1. And the square of the amplitude defines the probability of measurement across 0 and 1. And that is so important. So you see that a general qubit stores two values. One is this amplitude across 0, and one is amplitude across 1, unlike a classical qubit, which can only be 0 or 1. And this sign, which is a little bit taken from quantum algebra, you see there is an angular brace, and this angular brace is called a Kate notation. This is just to make you understand that when I write a state in terms of this particular notation, it means it's a quantum state. If I only write psi will be a classical state. If I write psi, then the psi will be a quantum state. So because in our computing algorithm, we can use both the classical and quantum states, where the classical states will be processed by a classical processor, and quantum states will be processed by a quantum processor. So in generic algorithm, we can use both the conventions, but when we specifically say it's a, then it's a, specifically it's a quantum state, okay? And as I show here, depending on the value of theta and phi, we can generate some of the very important states of qubit states. These are very important states of qubit states for the specific values of theta and phi, though I can have the infinite number of states across the surface of the Bloch sphere. But now if we come down to my previous discussion here, so what I understand is that a single qubit can now generate two values, or can store two values. So if I have two values in my data, I can use one qubit, because one value can be scaled and represent this part, and another value can be scaled and can represent this part. So two values can be stored in one qubit. And if I have two qubits, it's a tensor product. So I will have 0, 0, 0, 1, 1, 0, 1, 1 as the basis states. So I can store four values. N qubit system can store now 2 to the power n values. And this is the power of superposition of the quantum computer, which means that the computing capacity, see, the entire story of advancement in computing is basically increasing the computing capacity. We were in a 4-bit, 8-bit, 16-bit, 32-bit, 64-bit single core processors. Why? Because we tried to process more data, computing capacity. Then we moved from single core to multi-core. Why? Because the single core limitation is a maximum 32 bits or 64 bits. But if I can increase the number of cores, I can process more bits in a given amount of time. I can do parallel processing. So again, the computing capacity means how much amount of data I can compute in a given amount of time. So if you look into the computing capacity, it's still linear in classical, okay? If I want to make a 16-bit to 32-bit, I have to increase the registers by 16-bit more. ALU channels, ALU block 16 bits more. So it's a linear. If you want to increase the computing capacity, okay, by 2, you have to increase the number of cores by 2. If you have to increase the capacity by 4, ideally, you have to have a number of cores cross 4. So this is the way how it is done, okay? Now it's linear. It's multiplied by k. it's a linear. Okay, in the case of quantum, it's exponential. If you want to move from 16 qubit, 16-bit register, 16-bit classical register to 32-bit classical register, I need to only change in the quantum from 4 qubit to 5 qubit. Okay, 4 qubit can represent all combinations of 16 bits and 32, and 5 qubit can represent all combination of 32 bits. And it represents all combination. That's so important. But that's why the computing capacity in a classical computer, in a quantum computer, is exponential. And that's the power of the quantum computers. But having said so, okay, there are obviously certain limitations. Okay, and these limitations are that here we want more qubits, okay, to compute. Though they can generate exponential data space, but still have to increase the number of qubits. Okay, but the increasing the number of qubits, though required, increases the errors. Why? Because the qubit at that particular size or limits of matter are highly interactive. The more qubits you pump in your system, more number that the number of error probabilities, or the more possibility of error increases. And that's why this is a very trade-off problem. Okay, if you try to increase number of gates and number of qubits in a circuit, your errors will increase, and you need to have error correction process, which is a costly, and all these things are coming. So if you look into the present scalability of quantum computer, the people are doing a very good research in the domain of error, how to handle error in quantum okay, that means in the quantum system, right? And so the error handling is one of the very strong issue, that why we are not having a very, very expected quantum hardware as we require. We are going up, okay, but still we need to do something more. Okay, and the fourth point is that don't be under the misconception that every classical computing will be transformed to quantum computing. No, it's not like that. Like every classical computing is not machine learning, where we have the exact mathematical form or function or logical function. We don't require machine learning. Only the uncertainty part is handled by machine learning. Similarly, not all problems of classical domain will go to quantum computer. The problems where we can exploit the quantum superposition, where we can exploit the quantum entanglement, okay, those are the areas where we need to focus on that quantum computer is necessary. Other than that, classical computers will out there. So it is not that classical computer will be completely replaced by quantum computer. Though ideal any classical function can be represented as a quantum function, but the cost is huge. You will go into that cost when you require that. Okay, so that's the direction. So don't forget that it's not that everything will be quantum. It will be a classical quantum hybrid. There will be quantum accelerators, just like the FPGA accelerators or GPU accelerators we're having. CDAC in our country is working a lot on this domain. They are making the infrastructure so have the quantum accelerators. NVIDIA has already started that work. Okay, so these are the things which are going on. Okay, so I can give a little bit stop here, right? If anyone has any questions, and the next 20 minutes I will just accelerate a bit and try to close my lecture. Okay, so if there are any questions here, I can answer a bit. Yeah, anyone has any questions at this point of time? I will be happy to answer if anyone has any questions. Any questions from any one of you? What I discussed? You can also put in the chat box. My PPT is not visible.
Yes, now it is visible. Sir, I have a
Okay.
question. I just write the question in my
Okay.
chat box.
How might quantum computer change AI decision systems? Okay. So it is not part of this lecture, but I will obviously try to cover up with one lecture. So I will give a little bit of hint. So artificial intelligence is basically means at the present day of machine learning, artificial intelligence at present is not rule based, right? It's based on machine learning mostly. So machine learning means what? Fundamentally, machine learning means the machine learns the distribution of your data. You offer a training set, and that training set is learned by the machine. So that training set is a good representation of the actual distribution of your domain. If you have prepared if you have prepared this training set very well, okay, you represented the domain variations in the training set as same as the actual variations in the actual domain, and your machine learning model tries to absorb that distribution, right, and learn the domain. Means that when you give the same set of inputs, okay, the labels what you require to be coming out, we need to be have a very close to the levels what you have in the training data. So that means that it is learning the distribution. And I will just go after a few slides in my discussion that quantum computers, you can generate distributions at your will. Whatever distribution, there are two fundamental techniques by which you can generate distribution. Distribution, nothing but the orientations of the samples in the space. Okay, so the orientations of our samples in a space can be very well done at your will in a quantum computer. So probably a quantum computer can match the distributions much faster than a classical computer because it can search a space, exponential space in a linear time. Okay, right? And that's why the game that machine learning can be done better in a quantum computing corresponding to a classical computer. I'll just give a little bit of hint to that in this lecture, but maybe my actual core lecture, which comes on quantum ML, okay, right? I can offer it to any of the next sessions. Okay. Okay. So yeah. So any more questions from anyone here? Okay. If not, let me go to my presentation and try to focus on the lecture and try to finish it. So as I said that you already seen the vector psi. So okay, yeah. So the vector psi can be projected across different basis states. Measurement basis, not basis states, sorry, measurement basis. Okay, normally the measurement basis are Z and X. So those Z and X and Y, three basis states are there, three measurement bases are there, but normally we will take it from the from the Z and X. Okay, and if we like to see whether the qubits are related, as I said, that superconducting qubit is the most popular now. Okay, right, but there are other qubits like electronic qubits, like ion trap qubits. Okay, and right, and there are completely semiconductor based qubits with quantum dots where Intel is working a lot. Okay, so different organizations are focused on different technologies. See, all of the technologies have some advantages, some disadvantages, and yeah, let's see that which technology or which are the top 2 or top 3 technologies in the due course of time in quantum computing. Okay, I will just a little bit move on. Cryptography, information algorithms. Okay, these are the 3 main domains of quantum computing. In terms of quantum computing, okay, there are other areas: quantum sensing, quantum material, quantum communication, which I'm not touching here, which are not the part of quantum computing. Okay, so now I will look into the summary of what we discussed. Okay, so as compared to the classical system of computers, the data representation is 0 and 1. The gate representations of fundamental logic gates and or not XOR. Okay, NAND, NOR. Okay, in the case of quantum computer, these gates are called rotation gates, and 2-qubit coupling operations. So this is very important, okay? This is very important to understand that when we say that computing means that how we can update the state of a qubit. And the state of a qubit can be updated by rotation operations. Why? Because, as I said, right, if I want to update the state psi, if you consider this as psi 1, and if I consider another state psi 2 here, so the transition from psi 1 and psi 2 will be done by changing the angles theta and phi. And this means that either it rotates like this across the x, or it rotates like this across the z. So the rotation angles, okay, and it also do across y like this, which is actually summation of theta and phi, combining theta and phi. So either rotation across x, rotation across y, rotation across z actually changes the state. Okay, this is the, that's why I've seen Rx, Ry, Rz, which are the only rotational operations. Now, what are these xx, yy, zz? This xx, yy, zz are called controlled rotation operations or entangled operations, which means that here the rotation of a qubit across x or across y, across z will be done based on the value of the other qubit. So normally we say that controlled operations is that we say there's a control qubit and there's a target qubit. And all these control gates are basically 2-qubit gates. So control qubit value determines whether target qubit will rotate as per required. Okay, so when we give xx, it means that we have a control qubit, which is a value, and there will rotation across x-axis based on that value. So we pass a parameter of rotation and the value of the control qubit. And the value of the, if the control qubit is 1, then the rotation happens across x. If the control qubit is 0, rotation doesn't happen. So these are called control qubit operations. So fundamentally, the operations on a single qubit, on a quantum system, are only 2 types of operations. One are single qubit rotation operations and 2-qubit controlled rotation operations. And that's why, like the classical logic operations, primitive logical operations, quantum also have primitive quantum operations. Okay. And if you look into this operations, these operations are represented mathematically. Okay, as a unitary transform. Okay, and I'm not getting details of this. The only thing you have to look into this is that the size of the formations depends on the number of qubits it works on. Okay, normally, if you are working on a qubit size of n, your matrix dimension will be 2 to the power n plus 2 to the power n. So if we see all these matrix, you will see that these are 2 cross 2 matrix. So here n is 1. So which means that these are all single qubit operations. And these are equivalent to rotation operations across x, y, z, or across O, something like that. But there are 2 other things in the matrices. One is that the weights in each of the matrix indices are ideally complex numbers. They are of the form x plus iy. Generally, maybe for a particular gate your y is 0, so it's only x. Or maybe for a particular gate your x is 0, it's only I, and y is 1, it's only I or minus I. But you have to understand that generically these are complex amplitudes or complex coefficients. And the good point of complex coefficients is that if we just, if you just go back to your, complex number theory, any complex number x plus iy can be represented as r e to the power j theta. R is root over x square plus y square, and theta is tan inverse y by x. So which means that each of these coefficients, as their complex number x plus iy, I theta is represented by an amplitude and an exponential theta part. And there are two representations possible. Both the representations are there in differences. One, we decompose it into 0, 1, I plus I minus I. Another representation is we represent them with r e to the power j theta. So don't get confused. R is e to the power j theta is just one representation of x plus iy. Okay, so don't get confused. Huh? And we have 2 qubit gates where the and 3 qubit gates. So some of the 2 qubit gates like this, these are the primitive operations. See now, these are primitive operations in many technologies, and 2 qubit gates will be presented as 4 cross 4 matrices. Okay, so third, I didn't mention all the matrices. Okay, are unitary matrices. Unitary matrices means they will have a inverse. Their inverse is guaranteed. You know that all matrices doesn't have inverse, but if you take unitary matrices, your inverse is guaranteed, which means that if you compute with a matrix U on a vector psi and you generate psi dash, you can always get a matrix U inverse because you know U and U is unitary. So it's very easy to find the U inverse because unitary matrix will always have an inverse. Now U generated U operated on psi generated psi dash. Now if you operate U inverse on psi dash, what will happen? If you apply U inverse on psi dash, actually psi dash is U psi. So the actual transformation is U inverse U psi, which is I psi, which means that by applying the unitary transform of the previously operated gate on the resultant state, you can come back to the initial state of the qubit. And that's called the uncomputation or reversible computation, which happens in the quantum system. You can always uncompute your computing state by operating in a reverse order the inverse operations on the qubit, and you can just get back what you were in some previous computing steps. And this is very easy operation for rollback instead of utilizing rewrite in the memory in the classical computing. Okay, so these are some of the things which are very important in quantum, and this makes things very different algorithmically than the classical. Okay, so there are some qubit gates which are not primitive operations, 3 qubit gates which are not at all there. These are only logical gates. If you want to generate a Toffoli gate, you have to decompose it into a 2 qubit CNOT and some single qubit gates. Okay, and this is a functional gate swap. You have to implement this with some sequence of 2 qubit CNOT gates. There are some derived gates which are not primitively available, but you can use this in your logic and algorithm because ultimately there will be a compiler which will be decomposing all these higher level gates into the primitive logic gates, single qubit and 2 qubit gates available in the quantum system, and making your quantum circuit perfect, and then mapping the circuit to the actual physical quantum hardware. Okay, so I will just discuss this part. So as I seen that this is a superposition, as you know, I discussed in the discussion that this is a general n-qubit state. So an n-qubit state, there will be an n-qubit state can store all to the power n combinations. The coefficients will start from C0 to C to the power n minus 1, where the basic states will be all possible n-qubit states, which means it's a 2 to the power n state. Suppose I have a 3 qubit. So 3 qubit will have all the 8 basis states. 4 qubit will have all the 16 basis states. So an n qubit will have all the 2 to the power n qubit states. And this is a representation of a superposition. The only constraint is that the summation of the square of the amplitudes will be equal to 1, because ultimately all the probability, these squares are nothing but the probability of each of the basis states. And ultimately the sum of the basis states will be equal to 1. Okay. Now, if we come back to a little simple presentation, try to discuss what is entanglement. Okay, let's look into that. So If we give a toy example of two qubit states, one state is like this, and this state, this example, let me use the pointer, and this example state is well represented by a decomposition of two disjoint quantum states, two disjoint single qubit states, which is fine. So a two qubit state can be decomposed as a single operation of two distinct single qubit states. But there are other two qubit states like this. This is also a two qubit state because this defines a projection of 0, 0, and 1, 1, which makes it a two qubit state. But this two qubit state cannot be decomposed into single qubit states. Means if I could have found A0 B1 and C0 D1, then this state could have been decomposed into two single qubit states. But I cannot find any A, B, C, D which can generate this particular state once again. So these type of two qubit states or multi-qubit states, which cannot be decomposed into a combination of single qubit states, are called as very tightly coupled qubit states. And these are called entangled quantum states. So entangled quantum states are those quantum states where the qubits are very strongly coupled and you cannot dissociate them into multiple single qubit states. And this particular operation generates a lot of difference in the distribution. So this is the scenario, what I discussed up to this, okay? If you compare the classical bit, it can only store one state of n bit. If we come to the classic quantum bit, it can store 2 to the power n states due to their position orientations of the qubit. All of them are not, none of them are purely 0 or purely 1. Each of them represented a projection value on the 0 and 1. And so combination of all these qubits will generate all the possible basis states in a 2 to the power n basis states of an n qubit system. Okay. And these are all the operations what I said, okay? Rotation of the vectors by the primitive quantum single qubit quantum operations. And now I come to a little bit of machine learning, what Dr. That means okay, what Dr. Pritimai asked me, okay? So if we look into the distributions what the states generates, okay? The distributions of a single qubit transformations can be very good in terms of if I have a single qubit state, I can always generate a distribution of two values because single qubit states will store two values, 0 and 1. And I can have an equal distribution of 0 and 1 by making the vector just horizontal, and a horizontal vector will have equal probability on the 0 or 1, and that's a 50% probability. So the distribution using one qubit is a distribution of two states, and the orientation of the vector, very good orientation of the vector, will give me the equal probability of the two states in the distribution. Now let's move on. With a little bit bias, if I just move the qubit a little bit more, not the horizontal, exact horizontal, then, and I shift it more towards the north pole, which was the 0 vector, the vector shifts a little bit more towards the north pole, the 0 vector, then by rotation, then I have a 60-40. Now imagine a single qubit can generate all possible distribution of two states. It can generate 60-40, 70-30, 20-80 distributions. So a single qubit can learn a result of two levels. Okay? And the level percentage in the distribution will be 60-40. And you can orient the vector such as it actually learns the level. 60-40 distribution of the level. Okay? Now let us see that what happens when we use entanglement. Entanglement is a much more stronger thing. Okay? I'll just summarize it. So entanglement of two qubits. So any two qubit quantum system can generate a distribution of four states, four basis states. Now, very ideal distribution of qubit states means all probable four states are equal. Means all the two qubits are completely horizontal. So their probability of 0 and 1 is 50-50 for both the qubits. And so if we take a combined probability, it is 25-25 for 0, 0, 0, 1, 1, 0, 1, 1. And this is the first state. Now, if we try to make an orientation of 1, 2, or both, then I move from a very entangled state to a totally entangled state. So imagine that the two qubit can generate so many distributions. And try to now understand what an n qubit can generate. So your n qubit can entirely generate 2 to the power n training data. So if you have 4 qubit, you can work on a training data of 16, 5 qubit, work on a training data of 32, and so log n. So number of training instances and number of qubits requires a log n. And that log n will generate a completely capital N distribution. And that capital N distribution can be entirely mapping to your training set. Because the training set, if you have 4 classes, then depending on the training set, you can map the 4 classes into the distribution what training set gives you. And mapping of distribution, which is machine learning. And in quantum, we can do this by single qubit rotations, which are distribution, changing distributions by individual qubit orientations, and squashing distributions or disruptive distributions, which can be done in entanglement. Combining these two, we have a very, very good way to represent distributions in the quantum systems, using quantum systems. That's why quantum ML and learning in ML is so good. I will just stop here due to the limitation of time. I will continue. I'll have to continue, maybe a little bit of break. I'm not very well also, but I will have to continue this lecture maybe after a couple of weeks and try to give you more information on that. I will just stop this lecture by telling that status of quantum computing, yes, for the students, there are fantastic things going on all across the world, in India, in QM, okay? Fantastic things going on in the quantum hardware, okay? So you see that distributed quantum computing coming up. 153 qubits per chip they have attained. P chips and 1121 qubits are now available. Crossbill 408 qubits, Kokabuda 4158 qubits. So these are so good. And the distribution starts, okay? So you have to connect multiple QPUs. And they are coming up. This is all IBM's status, okay? Fantastic companies, software consultants which develop the softwares on the quantum hardware. Okay. Quantum computer manufacturers who are there. Element technologies in terms of superconducting qubit, dilution refrigerator, quantum control, lot many things are there. In our university, University of Calcutta, we are holding a workshop of from Keysight, which works on microwave control. That means, and they are supporting us in some of our projects. So, so you can come and you can join that. Yeah, I think the LinkedIn post is there if anyone is interested. I will send the link to Dr. Timon so that he can circulate it in this group. Okay, and this is on 10th and 11th of this month, right? At Rajavala Science College. The seats are limited, but still, I think some and a lot of initiatives have been taken at the government level and world level. Okay, a lot of problems. We are working with multiple problem spaces in this particular domain, and you can look into the very interesting problem spaces of simulation, optimization, machine learning, cryptography, and a lot of organizations are looking forward to work on these domains, and a lot of funding opportunities are available in these domains, right? So yeah, this is a tough domain, but if you can develop expertise, right, you can still do a lot of things, because still there are very few experts in quantum computing. Okay, and maybe if you get the training, and if you if you do your own hard work, right, you can be one of the experts in the next few years. Okay, so there are future direction of quantum hardware development. Yeah, this IBM roadmap, fantastic roadmap. And 2026, we are almost touching 5,000 qubits, and that's why this fantastic. Okay, and quantum HPC, as I said, NVIDIA I've already worked with, showed the benchmark results of GPU, QPU. CDAC has started their initiative in Bangalore, where they will integrate the quantum computer with their HPC, I think within a plan of 1 to 1.5 years. And we're all looking forward to that. Okay. Yeah, this is one of the very prestigious occasions for our group at University of Calcutta, where we received the IBM Research Access Award. Me and my PhD student Mrityunjay, who is now a principal quantum engineer at SL Technologies, he's just finishing his PhD with me now. So we received the quantum research access award for standing in India as a research group, and that's a very prestigious thing for us. And we have a fantastic team, and we are very lucky that most of the people have been absorbed by industry and very high level of research labs. So we have collaborations with most of the good universities across the world, most of the companies in India who works in quantum computing. So I didn't mention the Keysight. Actually, now Keysight is as a strong collaborator for us in this particular domain. Okay, and so yeah, so thank you all. These are research directions. A lot of things can be there. I will, yeah, the algorithms, fault-tolerant architecture, scalability, quantum software, integration with classical hardware. So a lot of things are there, and let's try to build up the quantum ecosystem in Bengal. Okay, with the help of the Science and Technology Department of Government of West Bengal and the state universities of the state. We have fantastic students, fantastic researchers across the state. Only some initiatives needs to be taken in a very fast pace, and if you can do that, yeah, I think the quantum researchers, if you see the density of quantum researchers in Bengal and Bengali, I think still is the highest in the India. So we are not very bad in this, right? Especially West Bengal, but we have to take a more initiative in the present challenging domains of quantum computer. And let's try to work together. Any help from my side? I'm not very well today, so I couldn't continue much further. But I will be I hope I will be fine with the next couple of weeks, and so we can again organize a discussion on that. Okay. So thank you all. Everyone can email it. And Dr. Pritimoy is well connected to me. And if there is any help from my side, you can route it to Dr. Pritimoy. Again, we can work together. Okay. So thanks, Dr. Pritimoy. Thanks to MAKAUT. This is the university from where I started. So I'm very happy. At that time it was WBUT, but now it's MAKAUT. But I'm still very happy that MAKAUT hosted me, and State Department of Science and Technology is also connected with this. And I think the Director of Technical Education of the Department of Higher Government of West Bengal is also connected with this. So I'm very happy that okay, this is a very well supported event from the government of West Bengal, all corners. Okay, thank you all, and stay connected, and let's do some contribution in the quantum computing domain. Okay, thank you all once again. And if any questions, I can still answer. Thank you.
So thank you, sir. Actually, if you have a question, you can type the question in the chat box, or you can raise your hand. If not, then it's time to conclude the session. I just give 1 minute. If you have a question, then raise your hands or type the question.
yeah. So I think there are no. So
Yeah,
I
I
think
think yes, sir. I think
if there are any questions, please get it and send it to me.
yeah, yeah.
I will try to
Exactly,
answer it.
exactly. Yeah, of course, sir, of course, of course, sir. So,
Okay.
sir, trying to conclude the session. So, thank you very much, today's speaker, Professor Chakraborti. He's
Okay.
my
There's
sir
one
also. Yeah,
one question. Okay.
yeah.
Discuss the reasons behind the significant. I said the reasons, right? It's a computing power. That's all in the first level, and then you can go on. A lot of things are there. Algorithmic speed up is there. Okay. But the first level is that the computing resource what you can get in terms of the search space, right? If you want to any computation problem is basically can be many. That is the most of the computation problems are optimization problems. And optimization problems rely on the search space, which means that in parametric space of the function, you try to find that which values of the parameters gives you the maximum or minimum value of the function. So ultimately, you have to search the space, the solution space of the function. Now, the quantum, the solution space of 2 to the power n can be generated by a resource of n qubit. And you can functionally, you can do the operation on all the spaces at the same point of time due to the parallelism of the quantum function or superposition states. So that gives you immense computing power, though the computing power a little bit fails when we try to sample the result from the distribution, because quantum computing converges to a particular basis states, right? When you try to do a readout. In order to do that, you have to take a little bit of cost in actually generating the amplitude of the basis state, which is your search state. Its amplitude is to be amplified a bit in some iterations, so that in the distribution sample, that sample is the highest probability. And then when you measure, you get the sample out. So that's the cost, what is there in the quantum algorithm to generate the sample in a proper amplitude in the distribution. That is the cost, but the cost of computing the best sample, that means is almost O1. And that is what actually works out, okay? Yeah, so computing mechanics says that you cannot measure the energy and the charge of the particle simultaneously. Okay, so basically, this uncertainty is being represented by the basis state uncertainty, what we introduce in the quantum communication, right? If you want to know the observable, which may be the charge of the state, right? Okay, right, and the axis, which gives you the measurement value, right? These two are not known. Okay, you can randomly try to connect to one, but the others will be missing out. So a proper understanding of a quantum state means that you need to know the vector value as well as the axis on which the vector was measured when it was actually sent for communication. Now in terms of the quantum state of an eavesdropper, right, you cannot get both the values. Either you try to see the vector, what is the value, but when you measure the vector, right, your basis is unknown. Or you randomly choose the basis to measure the vector, okay, but that measurement value will collapse, okay, because your basis was not proper. So this is the uncertainty which happens in the quantum measurement. So a particular sender and receiver, the Bob and the A, that means Alice, will only know what is the vector and what is the basis. Others, the Eves, will not able to know one of them. One of them it can guess, but guessing will not help them. Okay, yeah.
So,
Yeah.
any question? Okay, sir, I think that there is a question, so we can conclude the session.
Thank
So,
you.
I thank you, student speaker, my sir, Professor Chakraborti.
Okay, best book to start with. There's one question. Best book to start with is the Isaac and Nelson Chong. Okay, quantum. I think computing comes from Cambridge. That is the book, can be a very good start book. Okay, for all of you. Yeah. Yeah. So thank you, Pretty Moy. Thank you for this, for organizing this, right? And let's keep in touch. Let's make a quantum computing group in our state, because you are a very active researcher, I know. And so try to make a quantum computing active group. We can discuss some problems, and
Yes,
actually ultimately through the state DST we can, or through MAKAUT we can actually make a good quantum computing group in the state.
very good. Thank you, sir. Thank you, sir. Definitely, I will. So, actually, I think that today's his speech, you have learned a lot about this emerging technology, and also you know that all our lectures are being uploaded on our YouTube channel, Online MAKAUT. So, request all to subscribe for future access. So now the time for about your certificate, because today is the last lecture of our lecture session. So about the certificate, from tomorrow onwards, you will get a certificate link on your dashboard where you can click and download your certificate. But one thing that I have to mention, that we have decided that a participant can download the certificate only if their average attendance is at least 70 minutes, okay, throughout the lecture series. So now, just time to conclude the session. Again, say thanks all of you, and also myself. So definitely, I will try to inform our honorable Vice Chancellor sir regarding this initiative, that we can, if I give something, then of course I will try to do that. So now the time to conclude the session. Thank you very much. Good night.
Thank you all. Thank you. Good night. Thank you.
Sir, can we download the certificate today itself?
No, tomorrow onwards, because I have to calculate the attendance. Okay, today's
okay, thank you
attendance,
so much,
then,
sir.
yeah.
Thanks.